Hello, welcome to Electronics Education. This is Vincent Chang. Today we're going to start a new series on operational amplifier circuits. Inverting operational amplifier circuits, Part 1, Virtual Ground Explained. Let's start with a circuit, operational amplifier circuit, and the input signal Vi is going into the operational amplifier through a resistor R1. A second resistor R2 is connected between the output terminal and the inverting terminal of the op-amp. So this configuration is the closed loop configuration. And this circuit is called inverting amplifier. Inverting amplifier. Again, it's the closed loop configuration. There's a feedback. There's a connection between the output terminal and one of the input terminal of the op-amp. So it's the closed loop configuration. So let's start with an ideal model of the op-amp, operational amplifier. Remember, so several important characteristics of an ideal operational amplifier. For example, the input resistance is infinite. There's no current going into the op-amp. Also, it's the zero output resistance, which means the op-amp serves as an ideal voltage control voltage source. What kind of voltage control? What kind of control voltage is the differential input signal? The difference between the non-inverting VA and the inverting input VB. So it's got the differential signal is amplified by an open loop gain A. So A means the open loop gain of the op-amp. And in the ideal case, the A is infinite. A is infinite. So therefore, the VO equals what? According to this model, A times the difference between A and the B. So therefore, the VA minus VB equals VO divided by the open loop gain A. But in ideal case, as I just mentioned, the open loop gain A is infinite. So therefore, the denominator of the right-hand side is infinite. So VA minus VB should be equal to 0. So VA minus VB equals 0. So VA equals VB. What does that mean? VA equals VB, which means in the ideal case, in the closed loop configuration with an ideal op-amp, the two terminals voltage should be equal. The two input terminal voltage of the op-amp should be equal. So VA will be equal to VB. VA will be equal to VB. Let's go back to the circuit. The VA, again, is the non-inverting input. VB is the inverting input. The two input terminal of the op-amp in this kind of closed loop configuration should be equal. So we know that based on the circuit theory, if the two circuit nodes, the voltage of the two circuit nodes is equal, which means what? Which means it's a short circuit. It's a short circuit. But this kind of short circuit is based on two phenomena. It's based on two conditions. Number one, it's the closed loop configuration. There's a feedback again connected between output and the inverting input. And the second, if you learn the feedback in the future, then we will call this kind of feedback is the negative feedback. All right? So it's the closed loop configuration. That's the first criteria. The second criteria is the ideal op-amp. So based on these two criteria, closed loop and ideal, then it's a short circuit between the two input terminals. So this kind of short circuit, what we call is virtual short circuit. It's the virtual short circuit, which means they are not actually short circuit, but the result is that the two input terminals voltage are equal. In other words, the input terminal of the op-amp is not grounded, but the behavior, the voltage, if you measure the voltage, is grounded. So this type of the ground is called virtual ground. All right? So two terminology. Number one is virtual short circuit. The other one is the virtual ground. So the input terminal is actually a virtual ground terminal denoted by the VG. All right? So let's move on with the closed loop analysis. So since the inverting terminal of the op-amp is the virtual ground, is the ground, therefore we can get the I1, right? So I1 equals VI minus what? Inverting input divided by, based on the Ohm's law, divided by R1. So VI minus 0, which is the virtual ground, divided by R1. And also this current, because ideal input, there's no current going into the ideal op-amp. So the current flowing through the R2 will be 0 minus VO, which is the virtual ground, minus VO divided by R2. So the gain, the closed loop gain, which is defined by the VO minus VI, will be equal to negative R2 over R1. In other words, in ideal case, the closed loop gain will be determined by the two external resistors, right? So number one, the first characteristic is going in through the inverting terminal, so it's the negative. So it's the out of phase amplifier. The output signal will be out of phase with the input signal. So there's a negative sign. Number two, the magnitude of the amplifier will be determined by the two external resistors, R2 over R1. So the next question I want to ask you is, what's the input resistance of this kind of op-amp, of this inverting amplifier? The input resistance is defined by the resistance between the input terminal and the ground, the source and the ground. In other words, the resistance seen by the external source, VI. So what's the blue input resistance Rn? I wanted to pause for maybe a couple of minutes to think about the question I just asked you. What's the input resistance of this closed loop inverting amplifier? So what's the input resistance of this inverting op-amp circuit, operational amplifier circuit? So let me show you two types of approach. Number one is analysis by inspection. It's the analysis by inspection. So again, so what's the definition of the Rin, the input resistance? The resistance between the left-hand side of the R1 and the ground. But there's another ground called virtual ground. All right? So the resistance between the input terminal, the source, and the ground should be equal to the resistance between the source, the input source, and the virtual ground. All right? So the answer should be R1. You get it? You get it? Of course, you can set the input resistance is R1 in series with a short circuit. It's also a good explanation, illustration. All right? So either way, the answer is R1. But if you are the beginner, study this kind of circuit, you might be wondering, is this true? Is really that simple? So I still encourage you to use the second approach, which is derivation, just based on, you just derive this. So based on the Kirchhoff voltage law. So VI equals what? The first drop is I1 times R1. The second drop is a virtual short, right? So the VI equals I1 times R1 plus virtual short. In other words, the I1 equals Vi minus 0 divided by R1. And the definition of the input resistance is the input voltage divided by the input current. So Vi divided by I1 equals R1. So based on derivation, the answer should be the same as the one that we got from the analysis by inspection. So here's the takeaway. So number one, the closed loop gain is the inverting op-amp, so it's the negative, and its magnitude is determined by the two external resistors, right? R2 over R1. So negative R2 over R1. The second characteristic of this circuit I want to know is the input resistance. It's the input resistance of this inverting op-amp circuit is R1. So if you want to have an amplifier with a high gain and high also as well as the high input resistance, is this circuit a good candidate? Is this circuit a good candidate to have the high voltage gain and the high input resistance? The answer is no, right? Because if you want to increase the input resistance, the R1 should be as large as possible. But R1 happens to be in the denominator of the gain. And they are conflicting to each other when you try to pursue the high gain and the high input resistance at the same time. So if you are a designer use this kind of circuit, you should be cautious to have a mindset of trade-off. All right, the trade-off between the input resistance and the voltage gain to see which parameter you can sacrifice. All right, so this is one of the key concepts of this circuit, which is also a disadvantage of this circuit. All right, so we have come to the end of this lecture. Thanks for watching.